Okay, so we had 3 best paper awards talks. Now we are moving to best students papers. The first is by Jac Stade about boundary art gallery problem being in NP.
Okay, thank you. I'm Jac Stade. I'm a PhD student at the University of Copenhagen. I'm going to be telling you why the boundary art gallery problem is in NP. So the art gallery problem is this sort of classic problem in computational geometry. We're given as input some polygon, and we'd like to find some small set of guards. The polygon represents the floor plan of an art gallery, and we want the guards to be able to see everything in the art gallery without leaving any blind spots. So here we're going to be thinking about the decision version of the problem, where we just ask, is some set of k guards enough? Now, when I say the input to the problem is a polygon, what I mean is that I've given a sort of list of coordinates of the polygon, given as rational coordinates, but I don't place any sort of restriction on where the guards can be, other than that they need to be inside the polygon. And actually, there are examples known where we might even need irrational coordinates for the guards, even if the vertices of the polygon are rational. And we'll see an example of this in a couple of slides, but I'm getting a little bit ahead of myself because this talk is not about the standard variant of the art gallery problem. It's about a different variant. So there's a sort of framework of art gallery variants that I like, where the XY variant of the art gallery problem sort of restricts the guards to be placed in a set S, and sort of only requires them to see a set Y. So here X and Y are either the vertices of the polygon, the boundary of the polygon, or all the points inside the polygon. So the standard variant is then the point-point variant. The guards can be placed anywhere and they need to see everything. We could also have the point-boundary variant, where the guards can be placed anywhere and they only need to see the boundary of the polygon. So in this example here, well, previously I needed 4 guards, but now in this example, I can get away with 3 guards because they only need to see the boundary, so that it's okay that they leave a small gap here in the interior. And then finally, it's sort of the variant that I'm focused on for this talk is the boundary-boundary variant, where the guards only need to see the boundary and the guards must be placed on the boundary of the polygon. And so why do we care about this variant? Well, if we look at these 9 variants, here's what's sort of previously known about the complexity. We can see that if X or Y are the vertices, then this problem is sort of known to be NP complete. It's just becomes sort of a discrete problem in that case. But then the remaining 4 variants are continuous in some sense. And so it's less obvious that we can give sort of an easy to verify certificate for them. And in particular, the point-point, boundary point, and point-boundary variants are known to be complete for a complexity class called exists-R, which is thought to be sort of strictly larger than NP, maybe. And I won't give a sort of precise definition of exists-R here, but I will say that's sort of roughly what it means. Okay, well, exists-R is contained in P space, so at least these continuous variants can be decided in polynomial space. On the negative side, we sort of typically know that exists-R complete problems will sometimes require irrational coordinates, so I might need to place a guard at a coordinate like square root 2. And in fact, typically, you would need to use roots of arbitrary polynomials. So it might be worse than square root 2. It might be sort of the cube root of 2, or it might be the root of some quintic that's can't be expressed in terms of radicals. And even if I don't need irrational coordinates, even if rational coordinates are enough, I don't have a bound on the number of bits I need in a solution. So for example, there are sort of examples where in the art gallery problem, I would need to place a guard at an x coordinate of like 2 to the minus 2 to the n, which is going to require many bits to represent. And so we can see in this table, out of these 9 variants, up to NP versus exists-R, we know what the complexity of 8 of the variants are, and my contribution is to show that this boundary-boundary variant is actually in NP, meaning that it's NP complete. And this is somehow kind of tricky. So the first reason that this is a little bit surprising is that actually I show that you sometimes need irrational coordinates even in this boundary-boundary variant. So there's this polygon here, and you can guard it with 3 guards like this, and I show that this is the only way of guarding this polygon with 3 guards. And in particular, I need to place the guards at irrational coordinates. So this one at the left has a coordinate of like -√2, 0. So then the next question, I said for sort of exists-are complete problems, I could also get ∛2. So could that happen here? Could we have an example of the boundary version of the problem where we need to place a guard at ∛2 for an optimal solution? And the answer turns out to be no. So what I prove is that in any instance of the boundary art gallery problem, there is an optimal solution where the coordinates of all the guards are sort of no worse than the solution to a quadratic. So they can be written something like p plus q times √r, where p, q, and r are rational numbers with some polynomial number of bits. So how do I prove that? I guess you start by saying, okay, if I place a guard on the boundary of a polygon, I look at the visibility region of that guard as a function of the position of the guard, and the sort of coordinates of the visibility region will be given by these sort of fractional linear functions. So if the guard has coordinate x, then at least piecewise, the sort of endpoints of this visibility region will look like some function of form ax plus b over cx plus d, where a, b, c, and d are integers that depend on like the coordinates of the polygon. So if I have some guarding configuration and I look at the visibility regions, which I now think of as like functions of the guard positions, I sort of get some sort of constraint satisfaction problem based on like the combinatorics of these visibility regions. And I can see, for example, in this version, I want, in order for this to be a guarding configuration, I want the top of this green arrow to be above the bottom of the blue arrow. And so I get a constraint involving these fractional linear coefficients. And the sort of key observation here is that if I have any other, if I start with a guarding configuration, I get a system of constraints, and if I have any other solution to that system of constraints, then that should also correspond to a guarding configuration. So in order to sort of understand the complexity of the coordinates I need in a guarding configuration, I just need to know what is the worst coordinates I could need in this sort of fractional linear constraint satisfaction problem. And in order to get a bound for that, what I do is I sort of design a process for solving this sort of system of fractional linear constraints. And what I mean by a process is really sort of a circuit which takes as input sort of a set of constraints involving these fractional linear functions, and also like upper and lower bounds for each of the variables. And then this circuit is going to do some sort of logical and arithmetic operations, and it's going to output either yes or no, depending on whether or not there's a satisfying assignment with all the variables in these range bounds. And the idea behind constructing this circuit is constraint propagation. So if I have sort of constraints like x is less than or equal to f of y, and y is less than or equal to g of z, if f is a monotone function, then I can compose these to get something like x is less than or equal to f of g of z. Similarly, for monotone functions, if I have this type of constraint, I can take an inverse to move the function from one side of an inequality to another. And this is very useful for these fractional linear constraints because these sort of fractional linear constraints, ax plus b over cx plus d, that's monotone. It's either increasing or decreasing as long as we avoid the pole where the denominator might be 0. And they also form a group, so I can take compositions and inverses, and the coordinates don't get that much worse as I do this. And the sort of result that I prove is that this is kind of enough to refute an unsatisfiable instance of this constraint satisfaction problem. So if I have an unsatisfiable instance and I keep doing this, eventually I'll get sort of a small number of constraints that are obviously unsatisfiable for some definition of obviously. But the problem is that there's no bound on the number of steps that I need to do this. So this isn't going to be enough to create this circuit that I want because I can only prove unsatisfiability. I can't ever prove satisfiability. I would just keep going on forever and I don't know when to stop. So I need a bound on like the number of steps, but actually with this sort of thing, I can't get a good enough bound because I can have an example like this. I can have a constraint like x is less than or equal to f of x, where f of x is x minus epsilon for some small positive epsilon. And hopefully we can see like this is kind of silly. I mean, this is obviously unsatisfiable, but the composition operation, this sort of constraint propagation, is not very good at detecting this. All I can do is I can repeatedly compose this function f with itself many times, and if I compose it with itself sort of k times, then I'll get this constraint like x is less than or equal to x minus k times epsilon. And I'm going to claim that this is sort of obviously unsatisfiable only when this sort of error term, this k times epsilon, becomes larger than the range bounds for x, where it becomes larger than the difference between the upper and lower bounds for x. So in particular, k, the number of steps that I need, well, maybe I can even do it, log k steps by doubling. Maybe I can double the number of compositions with a single step, but the number of steps I'm going to need depends both on this parameter epsilon and also on the range bound for x. And so this is going to be bad if I'm trying to create this type of circuit. So the solution is that, okay, this function f is something relatively nice. It's a fractional linear function, and I can actually just compute the limiting behavior of what happens as I take the number of compositions to infinity. So if I ever see a constraint like this, like x is less than or equal to f of x, I'm going to just sort of see, instead of just repeating this function many times, I'm going to say I'm going to repeat this composition infinitely many times. And in order to understand the limiting behavior, really what I need to do is I need to compute the fixed points of this function f. And f is this fractional linear function. And computing the fixed points is just sort of solving a quadratic equation. So I get the fixed points end up being this sort of, end up being a form p plus q times square root r. And this is really where the irrational, coordinates come in this problem. And what I show is sort of that this is really only the only way that you can get irrational coordinates. So in particular, I can sort of now, with this extra infinite composition step and this constraint satisfaction, I'm able to get this sort of circuit which solves the problem. And you might hope that it would be like a polynomial-sized circuit or something like that. It's not. It's like n to the log n. But what really matters is somehow the depth, or really the arithmetic depth of this circuit. So the point is that the number of arithmetic operations that I do as I, on any path from sort of the input to the output, is only like log n. And now I want to use this circuit to sort of understand what the complexity of a solution is. And so what I do is I sort of vary the upper and lower bounds for this first variable x1. And what I am able to do, which takes a bit more work, but I construct this circuit in such a way that I can see that the output will only ever change when x passes through a coordinate of this form p plus q times square root r. So this means in particular that there has to be a solution where x1 has that form. And so then I can sort of fix x1 and repeat for all of the other variables. So this is called sort of a quantifier elimination. And I repeat this, and I'll find that I get an entire solution where all the variables have this type of form of p plus q times square root r. And because the sort of arithmetic depth of the circuit is only logarithmic, I will see that sort of p, q, and r have only polynomially many bits. So this type of solution, I also guess I have to show that I can sort of verify a solution like this. I can write it down in a small amount of space. I need to show that you can verify it efficiently, but that's true because you only have to ever sort of deal with two variables at a time. But this will prove that that I can solve this problem in NP. And so this shows that the boundary problem is in NP. Thank you for coming. That's my talk.
Any questions here? Yes.
Are there like higher dimensional extensions of this problem, like 3D?
Yeah, the art gallery problem certainly has variance in 3D. An interesting thing to note is that if you try to do the boundary variant in 3 dimensions, there are examples where like no constant number of guards is enough, or no number of guards is enough. You get weird things that happen in higher dimensions, but yes, they exist.
Yes?
So the result actually show that from more linear or from fractional linear programming in as well.
Yes,
Could you repeat the question?
okay, so just to repeat, the question is, do I show that this sort of fractional linear programming is in NP? And I guess the answer is yes, but I guess yes, I show that this constraint satisfaction problem where the constraints are fractional linear, sort of each only involving 2 variables, that's important. I show that's in NP, and in fact, I show that you can solve it in quasi-polynomial time.
Yes.
How do you find the square root to polygon?
Repeat the question.
Okay, thank you. So the question is, how do I find this polygon where I need square root 2? I think I don't really have time to explain that. Yeah, sorry.
Good and quick answer. So we don't really have time for more questions, but let's thank the speaker.